When we hear the keyword teleportation, our minds often leap to the fantastical imagery of instantaneously transporting matter from one place to another, as popularized by science fiction classics like Star Trek. However, the type of teleportation portrayed in these fictional universes remains beyond the realm of possibility given our current understanding of physics. Nevertheless, quantum teleportation, a fascinating and real scientific phenomenon, has achieved what once seemed unthinkable. While it doesn't involve transporting physical objects, quantum teleportation allows for the transfer of quantum information, such as the state of a particle, over potentially vast distances. Quantum teleportation might sound like magic, but it's deeply rooted in the laws of quantum mechanics. The process leverages quantum entanglement, one of the most intriguing aspects of quantum theory, to teleport the state of a particle to another particle, even if they are separated by great distances. This technology, which was once purely theoretical, is now being demonstrated in laboratories worldwide. The implications are profound, ranging from advances in secure communications to building a robust quantum internet. To grasp quantum teleportation, we first need to understand the concept of quantum entanglement. In quantum mechanics, particles can become entangled, meaning their states are interconnected in such a way that the state of one particle directly affects the state of the other, no matter the distance between them. This connection allows information about a quantum state to be transferred without physically moving the particles. Unlike classical communication, where information is transmitted by sending a signal from one point to another, quantum teleportation transfers the quantum state of a particle. For example, scientists can transmit the spin state of an electron or the polarization state of a photon from one location to another. This process involves three main steps: two particles are entangled, and one of these particles is sent to the receiver while the other remains with the sender. The sender interacts with the particle whose state is to be teleported and performs a joint measurement on this particle and their entangled partner. This destroys the original state but generates classical information about it. The classical information is sent to the receiver, who uses it to transform their entangled particle into the state of the original particle. This process doesn't violate the laws of physics because it relies on classical communication to transmit the measurement results. Since classical signals cannot travel faster than the speed of light, quantum teleportation doesn't allow for faster-than-light communication. Quantum teleportation has its roots in theoretical work dating back to the early 20th century when scientists like Albert Einstein, Boris Podolsky, and Nathan Rosen proposed the concept of entanglement in the famous EPR paradox. This paradox questioned whether quantum mechanics could be a complete theory, as entanglement seemed to defy classical intuition. The idea of quantum teleportation was formally introduced in 1993 by a team of scientists led by Charles Bennett. Their groundbreaking paper demonstrated that quantum information could be transferred using entangled particles and classical communication. This theoretical work paved the way for experimental demonstrations. In a milestone experiment, a team led by Anton Zeilinger successfully teleported the quantum state of a photon across a laboratory. This marked the first practical realization of quantum teleportation and opened the door to more ambitious experiments. Researchers began extending the range of quantum teleportation. By leveraging optical fibers and free space transmission, they teleported quantum states over distances exceeding 100 kilometers. A Chinese team used the MISHA satellite to achieve quantum teleportation between ground stations separated by 1,200 kilometers, demonstrating the feasibility of space-based quantum communication. Entanglement is at the heart of quantum teleportation, yet it remains one of the most mysterious phenomena in physics. Einstein famously referred to it as spooky action at a distance, as it suggests an instantaneous connection between particles regardless of distance. Experiments have consistently confirmed the existence of entanglement, even across macroscopic distances. Entangled particles behave as a single system, meaning that the measurement of one particle instantaneously affects the state of the other. This property enables the transmission of quantum states, although it's important to note that entanglement itself doesn't transmit usable information faster than light. Quantum teleportation has rapidly evolved, with several groundbreaking advancements in recent years. Some of the most notable include: photons are ideal for quantum teleportation due to their speed and resistance to environmental disturbances. Experiments have successfully teleported the quantum states of photons over optical fibers and through free space. Beyond photons, researchers have explored teleporting the states of atoms and ions. These experiments are more challenging due to the complexity of manipulating massive particles but are essential for developing quantum computing systems. One of the challenges in quantum communication is maintaining entanglement over long distances. Quantum repeaters are devices that extend the range of teleportation by creating new entangled pairs along the communication path. Advances in nanotechnology have enabled the development of integrated quantum circuits that can perform teleportation on a chip. This miniaturization is crucial for building scalable quantum networks. While quantum teleportation doesn't transfer physical objects, its ability to transmit quantum information has profound implications. Some potential applications include: quantum teleportation can enable secure communication by ensuring that encryption keys are exchanged without the risk of interception. This technology could protect sensitive data from hacking and eavesdropping. Quantum teleportation is a key component of quantum computing systems, allowing qubits to be transferred between nodes in a quantum network. This could enable the development of distributed quantum computers capable of solving complex problems. A global quantum internet would rely on teleportation to transmit quantum states between distant nodes. This network could revolutionize fields ranging from finance to healthcare by enabling ultra-secure communication and data sharing. Quantum teleportation experiments provide a unique window into the nature of reality, helping scientists test the foundations of quantum mechanics and explore new physics beyond the standard model. Entangled states are highly sensitive to environmental disturbances, making it difficult to maintain them over long distances. Quantum systems are prone to errors due to noise and imperfections in measurement devices. Developing error correction methods is critical for practical teleportation. Building large-scale quantum networks requires creating and distributing entangled pairs on a massive scale, a feat that is currently beyond our technological capabilities. Quantum teleportation requires classical communication channels and entangled resources, which can be resource-intensive to establish and maintain. Looking ahead, quantum teleportation is poised to become a cornerstone of future technologies. Ongoing research is addressing the current limitations, and several exciting developments are on the horizon. Expanding on the success of satellite-based experiments, researchers are planning to deploy a global network of quantum satellites to enable secure communication across continents. Quantum teleportation could facilitate the development of cloud-based quantum computing platforms, allowing users to access powerful quantum processors remotely. In the future, quantum teleportation could play a role in space exploration by enabling secure communication between Earth and distant spacecraft. Combining quantum teleportation with artificial intelligence could unlock new possibilities in data analysis, optimization, and problem solving. Quantum teleportation raises profound philosophical questions about the nature of reality, identity, and information. If information can be transferred without physical movement, what does this say about the fundamental nature of the universe? These questions continue to inspire scientists and philosophers alike, driving both technological innovation and intellectual exploration. Quantum teleportation represents a remarkable convergence of science fiction and reality. While we may never achieve the type of teleportation envisioned in Star Trek, the advances in quantum teleportation are transforming our understanding of the universe and paving the way for revolutionary technologies. As researchers continue to push the boundaries of what's possible, the dream of a quantum-connected world comes ever closer to reality. Please like, share, subscribe and comment. Thank you for watching my channel.